Good morning and welcome to the second day of the American Gem Trade Association's Dynamic Seminar Series, sponsored by the American Gem Society. Dr. James Shigley is a distinguished research fellow at the Gemological Institute of America in Carlsbad, California, where he helps direct GIA's research activities. Prior to joining GIA in 1982, he studied geology as an undergrad at the University of California, Berkeley, and later received his doctorate in geology from Stanford University. Joining Dr. Shigley will be Dr. Aaron Palke. Dr. Palke developed an interest in minerals and gemstones, searching for agates and other minerals in eastern Montana. He pursued a formal education in geology, obtaining a Bachelor of Science degree from the University of Tulsa and a PhD from Stanford University. Stanford seems to be very popular. He began his gemological career as a postdoc research associate at the Gemological Institute of America, where he is now the senior manager of colored stone research. In this role, Dr. Palke leads GIA's research efforts into geographic origin determination for rubies, sapphires, emeralds, and other colored stones, as well as improving criteria for identification of treatments for colored stones. Dr. Palke is a regular contributor to Gems and Gemology, serves on the journal's editorial review board, and has acted as a guest editor for 2 special issues of the journal so far. Joining Dr. Shigley and Dr. Palke is Wim Vertriest. Wim is GIA's manager of field gemology and has participated in GIA field expeditions on different continents, focusing on colored gemstone mining areas to collect samples for GIA's research. Wim oversees the Field Gemology Department and is in charge of GIA's colored stone research collection in Bangkok. He graduated from the Catholic University in Belgium and obtained a master's in geology in 2014, specializing in geodynamics and geofluids, and gained his FGA and GC diplomas. Wim has been working at GIA since 2015 and has authored and co-authored articles on new gemstone localities, updates on existing mining localities, in-depth gemological studies, and treatment experiments. Please give a nice, warm welcome to Dr. James Shigley, Dr. Aaron Palke, and Wim Vertriest.
I can't see any of you out there, so I hope you're there. I'd like to thank you for coming out this morning and spending your Tucson time with us. I'd also like to thank AGTA, the organizers, for this opportunity. I'm here with my 2 colleagues. They're really more expert on this subject than I am. But we all know how important origin reports are in the colored stone trade. And what we'd like to do today is try to look behind the curtain at GIA about the scientific approach we take to make this origin determination. So just a couple of introductory slides. These are the stones, and actually there are a few others that we currently provide origin reports on. I think the other ones you had on your list were jade and opal. Right? What were the other ones? Demantoid and peridot. So there are a couple of other stones that we are providing origin reports today in addition to the ones I've shown. It's important to remember an origin report is an expert opinion based on documenting the properties of the gemstone at the time we examine it. And it's based, of course, on the expertise and the experience of our staff gemologists. And I would say, of course, that origin reports present quite a number of challenges for our laboratory and any laboratory that offers this type of report service. This is kind of the concept, it seems to me, just using sapphire. Certain stones are valuable, and I think it's kind of a combination of color, quality, and rarity. Certainly the remote region of Kashmir has been has historically produced some very fine, most valuable sapphires. But because the production only lasted for a short time, maybe about 10 years in the 1880s, and then it really pretty much came to a stop, high-value gem material from this location can reach very high per carat values. Well, let's say we have a different situation. We have 3 blue sapphires from 3 places, 3 locations. Deposits in different countries can produce similar, very similar material. But despite their similar appearance, these sapphires oftentimes would be valued differently in the trade. So again, they have color and quality, but now I've kind of indicated relative rarity, or as I said at the bottom, kind of perceived rarity. What do I mean by perceived rarity? That's rarity in your own experience. I haven't seen many, so they must be rare. So again, I think we're in kind of an interesting time of, assigning value based on geographic origin and maybe forgetting the color and quality aspects of gems. There's some underlying concepts that kind of form the basis of origin reporting. Properties and compositions of colored stones are in part the result of the geologic conditions of their formation in whatever country they occur in. And of course, you're kind of making, in a simple way, the assumption that on origin reports that colored stones from different places would have different features. That is true in some cases, but it's not always true. And finally, of course, some deposits in certain countries are famous for historically producing gems of very high value. So in order to make an origin report, there are a couple of requirements. You need to have characteristics of the colored stone that are unique for different deposits. And you have to be able to document or measure or do something with those features in a routine basis in a laboratory setting. You also need to have gems and a sample database of information, gems of known origin, gems where you know exactly where they've come from, because you're going to document those reference stones, and then the client stone, when it comes in for a report, is going to be compared to those reference stones. If you don't have reference stones, I guess the analogy would be kind of like a D to Z color grading without master stones for diamonds. You know you're on the D to Z scale, but you don't know where you are. Well, again, you need references, in this case, colored stones from major deposits, so you can compare the features of the client stone to the reference stone. And again, the origin conclusion is an expert opinion. So we're going from the characteristic features that we're documenting and trying to infer, kind of going upstream to where this may have come from. I just show you here that there are some really distinct geologic environments of gem formation. Colored stones form in different crustal environments at or near the Earth's surface, maybe at depths of 60 to 70 kilometers. It's kind of really known. And of course, I show a sapphire and basalt and an emerald in a hydrothermal vein from Colombia, a topaz and a rhyolite from Utah, and a ruby in a metamorphic rock from Australia. At the surface, these primary host rocks oftentimes weather and decompose, which releases gems into the secondary environment, a river or alluvial deposit. And of course, at that point, oftentimes the original host rock no longer exists. So we have these geologic environments at or near the Earth's surface that are producing gem material. And again, it's the geology of the environment that's going to impact going to influence the properties of the material. So the geology presents some challenges for origin determination. The geology of the deposit may not be well known. Access for sample collection at that location may be difficult or impossible. So the geology of some of these places, especially in far away remote areas of the world, may not be well known until someone actually goes there and makes that study. Similar gem deposits can be found in different countries, and conversely, different gem deposits can be found in the same country. So, of course, some gem deposits cross country boundaries. The country boundary is just kind of an artificial agreement. There's no line on the ground. And of course, as I said a moment ago, many gem deposits represent secondary alluvial occurrences in the host rock. The original host rock is entirely absent. And having the host rock is a good source of information on the conditions of formation. As far as I know, origin reporting began in the 1940s by the famous Swiss gemologist Edward Gubelin, who began issuing letters or kind of reports on the colored stones being sold by his family business in Lucerne, Switzerland. So it goes back many years. But in the 1940s, I just kind of tried to list kind of the likely ruby sources at that time. Afghanistan, Cambodia, India, Myanmar, Thailand, Sri Lanka, Tanzania. There was kind of a relatively small number of sources of rubies at that time. And because of the geology, they kind of had different features, different inclusions and such. Well, the challenge today is a little different. One more talk. You all know, I think you're all familiar with Edward Gubelin made significant contributions to gemology, particularly in the area of microscopy and photomicrography. He started writing about how inclusions in the 1940s, how inclusions could be used as a means of gem identification. What's the host gemstone? But again, he also made it go a step further that these inclusions are going to tell you something about the environment the rock, the gem formed in, and perhaps would be characteristic of the specific locality. So by connecting the inclusion features, and he was primarily making, I think, this determinant of origin on inclusions, by connecting the inclusions with the geologic origin of rocks, this work kind of provided the basis of colored stone origin reports as we know today. Well, part of our challenge today is there are more ruby localities. I listed, and there are kind of a whole bunch of them. Now, you might say, I've never seen high-value rubies from any of these places. And that's probably true. But I think if you're in a laboratory environment and you get a stone brought in from a client, and you have to say, I've never seen a nice ruby from this place, so I can ignore that place. You cannot make that assumption. You kind of have to have all these places in mind because they all, in theory, have the potential of producing high-value material. So again, you can't just dismiss places because you've never heard of material from there. I just wanted to turn this over to my colleagues in just a minute, but I wanted to say just a little bit about diamonds, origin reporting on diamonds, because we get asked this question a lot. Can you give an origin report on a diamond? I would say quickly the answer is no. We now are aware from recent studies that diamonds are forming in two environments, in the crust of the earth and the upper mantle. On the top left of this is the most common occurrence near the base of the lithosphere, the solid outer layer of the earth, where the diamonds are coming from about 100 miles down and are come up by these kimberlite eruptions. And now we know from recent studies at GIA and elsewhere that there are diamonds that are coming from much deeper in the earth, maybe 300 or 400 miles down along subduction zones where you have the crustal rocks going down into the mantle and melting. And we now know that there are diamonds, unique diamonds that are coming from this very deep environment. But wherever they come from, the diamonds have a deep earth kind of mantle signature. The properties are a signature of these conditions. They don't have features that are characteristic of the crust because they didn't form in the crust of the earth like a colored stone. They form much deeper, so they have no crustal rock signature. They're only in the kimberlite for not very long. I think geologists now believe that these kimberlite eruptions are very rapid, so it might only be a few weeks to go from 400 miles down up to the surface or something. So there's not much time that they're sitting in the kimberlite to have any signature put into the diamond. And once they get at the surface, they're fine. There's nothing going to change them except perhaps radiation exposure producing some color defects. So there's no country signature that we can know of. So, as I said, can you determine the origin of a diamond? The answer is no. Market values of diamonds are based on the 4 Cs, not where they come from. That's because you can get high-quality diamonds from any location. And unlike colored stones, which form near the surface relatively, diamonds form in a much deeper, more chemically homogeneous geologic environment. There's some real challenges if we're going to see if we can solve this problem. The biggest challenge is there's no representative collections of diamonds from all the mines in the world that are available for scientific study. And of course, some of that scientific study may involve some sample damage. So there are no collections of diamonds from all the mines, even if you had a bright idea that you might solve this problem. There are no collections that are available for study. There are no diagnostic visual features inside the diamond. The inclusion features all are as a result of formation deep in the earth. Any surface appearance or unique surface features of the rough crystal are going to be cut away in manufacturing. They do contain trace elements, which my colleagues are going to be talking about. Trace elements are a possibility, but their analysis is difficult. And again, they give you the trace elements in the mantle, not the country where they're found. So I say the prospects of diamond origin determination are unlikely. And if you hear of an article or a company saying, we solved this problem, we know how to tell where diamonds come from, I would be skeptical. So the only thing we can do is really kind of follow the diamond from the rough state to the manufacturing process to the cut stone. So we issue origin reports, but I think that's a kind of a wrong name. We're just matching a rough and a cut stone. So again, we're kind of inferring an origin based on mapping a rough diamond coming to us from a client mine from a particular source, and then the diamond goes out, goes manufactured, comes back, and we're saying, can we match this cut stone to this original rough crystal? So it's kind of, in a way, the opposite direction of inference. We're going from a rough diamond from a known source to give you a kind of an origin statement. And this number is a little dated, a couple of years, but I think as about 2 or 3 years ago, we've done about 90,000 of these origin reports, just to give you some sense of this effort. With about a 90% success rate, that means we can match the cut stone with the rough crystal. And for the other 10%, we say we can't match, and that's the way it is. So with that, I'd like to turn it over to Wim, and now you'll hear from the real experts.
Now that's a tough act to follow. So I think we all understand now that origin determination has a complex history and is continuously evolving. So we just heard about the little sidestep to diamonds, but we're going to go back to colored stones now. So me and my colleague, Dr. Palke, I'm really going to focus on what's going on in the laboratory and how we address this from a more practical viewpoint. I think some of you were in the audience yesterday when I spoke about field gemology, so some of these slides might look familiar now. But I want to start with saying that GI services and reports, whether that is an identification report, a treatment detection, or an origin report, those are all built on research. Research is the foundation for all of these things. We don't just go out and guess these things. But what does that mean, building all of that on research, building origin determination services on research? When you talk about scientific research at GIA, for me that consists of 3 pillars. The first one would be that you need qualified, experienced staff. I think this image, this gentleman might look a little bit familiar. To speak about experience, this is a photo that was taken the year I was born, which says maybe more about me than it says about Dr. Shigley. But it definitely is a testimony to his experience, and I think his qualifications, we heard it from Gary before. Then the second part is the equipment and instruments. Equipment and instruments are critical. We see gemology evolve at an incredible pace where a lot of new instrumentology is coming in. Now, that doesn't mean that all that instrumentology is critical. To this day, the most important tool in a gemological laboratory is the microscope, the exact same tool that Dr. Gublin was using in the 1940s when he started doing origin determination. But when we talk about equipment and instruments, it is probably more important that instead of having the instruments, is knowing how to use these instruments correctly. Because in this day and age, every idiot with $20,000 can go buy a spectrometer and start printing wiggly lines. That doesn't mean anything. You need to be able to interpret these things, calibrate them correctly, use them correctly. I would trust any qualified gemologist with a 10x loupe over an idiot with $1 million worth of equipment. And then the third part is probably the most overlooked and probably the most important part. And that is, even if you have an army of PhDs in geology, preferably from the Stanford team, $1 billion worth of equipment, if you have all these people do their research, if they don't work on reliable samples, it is going to be a waste of everyone's time. If you do a study on Nigerian sapphires and you're not even sure that your sapphires are from Nigeria, what the hell are you even doing? So these reliable samples are underpinning a lot of that research that we are doing at GIA, and that is where field gemology comes in. But what makes a sample, a collection reliable? And I'm going to use a quote here from someone who's got way more credibility than I have, and that is Sir David Attenborough, who in a documentary about museum collections said the following thing, that a research library associated with collections is almost of greater importance than the gemstones themselves. Unless you know where the gem came from exactly and when it came from exactly, you're missing a lot of very, very important information. And that information does not only come from the gemstone itself, but from the circumstances of documentation that should accompany every scientifically collected gemstone. What he's basically saying here is, if you collect a bag of gems, all you have is a bag of gems. That is not a reliable collection. Building a reliable collection in the field kind of looks like this. You go out and you collect stones, and you do that where the stones are. If you want to collect reliable spinels from Tanzania, from Mahenge, the best place to get it from is right here, from the Mahenge, the valleys in Mahenge, where you can find the spinel directly from the rock. But realistically, so we've done that over 100 times, going to all these places around the world. I think this is a map where you can get an idea of all the places we've been to, where you can see a very heavy focus on Central Asia, Southeast Asia, and East Africa, where a lot of ruby, emeralds, and sapphires are coming from. But going to the fields, going where the stones are also means this, because 1 week a year, most of the gemstones in the world are in Tucson, Arizona. But I think we can all intuitively understand that there's a different degree of reliability there. If I collect stones at the mine, like this little emerald that I took from the rock in Ethiopia, it's going to be a lot more reliable than the stones I collect in Tucson. I think we all understand that. And to reflect that in our collection, we developed a classification system. Because if you know the reliability of your stone, if you know how much you can trust the label, that will be critical to interpret the data you collect on those stones. So that is why we have a classification of A to F of how reliable those samples are. An A-type sample would be that a GIA gemologist mined the stone themselves. I can be 100% sure that that stone is actually from that place and that it is untreated. Here we are hammering Paraíba tourmalines directly out of the host rock. In an ideal situation, all of our samples would be like this. I take my hammer, hit a rock, 10-carat ruby comes out. Fingers crossed that that ever happens, but we keep trying. A B-type would be that a gemologist has witnessed the mining. I've seen the stone come out of the ground. For those of you that had the privilege to visit gem mines, very often they ask you to keep your hands in your pockets, because you could pick up one little rock and walk out with $1 million. But witnessing the mining is already a big step. So here we see this guy who is picking opals out of the tailings in a mine in Brazil. So we are still pretty sure where these stones are from, pretty sure that these are untreated. Then we have a C-type sample, where we collect them from the miner at the mine, but I haven't seen them come out of the ground. So here we are at the large-scale ruby mine in Mozambique, where we are in their sort house. We are still at the mine site, but these stones might have been mined the day before, the week before, the month before, but they haven't left the site yet. But I still know where they came from. But we can already feel we're a little bit more disconnected from the actual mining here. Then a D-type sample would be that collected from the miner, but not at the mine. These gentlemen we met along the road in northern Kenya, where they brought parcels of sapphire to us that said, we've mined this over the last couple of weeks over there somewhere. So I don't have a specific GPS coordinate of where this comes from, but I got it from the guy who claims that he took it out of the ground himself. So this is a D-type sample. I think we can already feel this might have been a mix from different pits. They might have brought stones in from somewhere else. Maybe they've heat-treated these overnight. So already a little bit less reliable, but you can see that there's a large volume of samples available to us there. So it's very convenient to build up your collection there. An E-type sample would be collecting from a trader in the local market. So here we are in the local market, collecting it from someone who is not the miner. So here I am working with this dealer in training in the market in Vietnam who drove a very hard bargain for those spinels. But we can already see this might be a mix of different goods. In fact, in some of these parcels, we were able to see synthetics and things like that. But you can see that the amount of material that's available to us there is very convenient. And then we have an F-type sample. Oh, there we go. It's collected from a trader in the international market. Here we have a complete disconnect from the source. We're in a different country, a different continent. Basically, by definition, almost every stone that we would collect for our collection here in Tucson would be classified as an F-type sample. It is very convenient to see a lot of stones. We have a lot of access. I can go see the Brazilian Paraíba dealers, the Colombian emerald dealers, and the Sri Lankan sapphire treaters in 45 minutes. If I had to visit them all at the mines, that would probably take me 6 weeks. So it is very convenient to collect it, but that doesn't mean that the reliability is the same. So that's why we have that A to F classification on there. That it doesn't mean that this sample is less valuable. We just have to see it in a slightly different context and interpret that data a little bit different. So this is basically the composition of our collection, where we can see that the vast majority of samples are D and E-type samples. So collected from the miner, not at the mine, or in the local market, because that is just the place where you get a lot of access to stones. Ideally, you'd want all of them A-type, but that is extremely complex and demands a lot of resources. But we do try to couple everything back. As long as your F-type sample matches your A-type sample, you can be pretty sure that your F-type sample is actually valuable. This is an idea of the composition of our research collection at the moment, where you can see that it is dominated by the corundum varieties, rubies and pink sapphires, blue sapphires, a little bit less fancy sapphires with a heavy focus on yellows. Spinel and emeralds are a little bit less. Why is emerald a lot less? Because the questions being asked about emerald are more straightforward. Treatment detection in emerald is pretty straightforward. Origin determination in emerald is not as complex as it is for blue sapphire. That is why blue sapphire is such a prominent part of our collection. And in the last couple of years, we've started adding a lot of these other stones. Like Jim mentioned, we're doing a lot of origin determination on jade, alexandrite, demantoid, Paraíba tourmaline, opals. So we're putting a lot more effort on those stones, collecting those stones, adding those stones, getting all the data on those stones in the last few years. But how do you go from those samples to an actual collection? Because the information does not only come from the object itself, but from the documentation that should accompany every scientifically collected specimen. That is how we start building that collection. But how do you create and maintain and turn that into a real reliable collection? Going from collecting samples in the field to turning it into a collection. Every single stone we collect gets entered into a digital database, which all of our gemologists worldwide have access to. So that includes a color-calibrated photo, so we know what color it is. That includes a lot of information of where we got it. And then when we start collecting data on it, we add that to that same database, which gives us the opportunity that someone who is sitting in the Tokyo lab, for example, could digitally be looking at a ruby that is physically in Bangkok. Because all the data on that stone, the FTIR spectra, the UV-Vis spectra, the basic properties, inclusion photos, chemical analysis, is available to that gemologist over there. So this is how we tag those stones. I got the example of that little emerald that we saw earlier, that A-type sample that I collected from the rock. That stone is now in our collection, and we see that that is all the information that's attached to it. It has a sample number, it has the name of these things. And the moment we start collecting data to it, it gets added to it. So that's how we turn that little sample that I collected in the field into a reliable sample that's a part of our colored stone research collection. Now, of course, we are collecting rough stones in the field. Rough stones are not ideal to do a lot of analysis on. There are a few tests that you can do on a rough stone, but usually you would like to have at least a polished window in there. For example, you cannot take an RI, a refractive index, on a rough stone. But also if you want to observe inclusions, if you want to do spectroscopy, you would prefer to actually have a polished window in there. So a big part of the field gemology team is also making sure that all of our samples are ready for analysis. They are ready to do all the spectroscopy, and that's why we use precision faceting equipment to get the correct orientation and the correct polish on all these stones so we can observe the inclusions, collect high-quality spectroscopy, collect high-quality chemical analysis without interference from whatever might be on the rough surface. And a big part of that is also orienting stones. Because we know that rubies and sapphires and emeralds, which are the core of our collection, they are dichroic, which means that if we look at them in different directions, they're going to have different properties. That is why we see a sapphire as blue or as green. So it's important for us to know which orientation we're looking at. Are we looking at the green axis? Are we looking at the blue axis? So that is a very important thing for us as well, that we have to make sure that we compare apples to apples, blue axis to blue axis, and pears to pears, green axis to green axis. Because if you start mixing these things, you're going to get very conflicting results as well. So that's why we have this instrument that allows us to align these things. That is a custom-made in-house instrument where we are able to align all those stones, determine the exact orientation of every sample, which helps us a lot for our spectroscopy ends especially. So that is it for the GI reference collection, which is a well-documented collection where we have an important stress and focus on geographic origin and treatment status. That is what we care about most. And that is what separates this collection from many other gem collections in the world. We do not care that this is the biggest and most beautiful and rarest stone. We care about how much can we trust the origin and how much can we trust the treatment. And that is what separates this collection from a lot of museum collections, for example, where they want beautiful big sapphires. I wouldn't mind having the Hope diamond in our collection, but that's not going to be reasonable, and I don't expect that because I'm going to chop it into little pieces anyway. And that would be a shame for everyone.
That would be hopeless.
Exactly. That would really bring that curse come to life. On top of that, that entire collection is used to support research. Research projects like locality descriptions, treatment experiments, but also more experimental procedures. Every single stone in that collection, if you make a good enough case, you can destructively test it, which is something that we have done for quite a bit of stones. Looking at new techniques, looking at more in-depth analysis that at this point we cannot do non-destructively. So I'm going to turn it over to Aaron, who's going to focus really on how we are doing the origin determination in the lab when a stone comes to the lab itself. There you go.
Is this on? Yes. All right. So after we built the collection, after Wim's been out in the field for 6 weeks or 6 months of a year, getting dirty and finding stones, we have to figure out what we're going to do with those stones and all the data he's collected on the stones in order to determine origin on the gems that are being sent to the lab for origin reports. Now, Jim also kind of touched on this a little bit, but really, when we're thinking about origin determination, geology is key. So the hope is that if we have a ruby from 2 different deposits, or 2 rubies from 2 different deposits, we're going to hope that the geology was distinct enough from those 2 deposits that it imparted distinct properties on those 2 stones. And we'll be able to tell the difference between stones from those 2 deposits based on those different properties. So as an easy example, we can think about Burmese rubies versus Siamese or Thai rubies. Back in the day when Gublin was kind of starting origin determination, these were really the main sources of rubies out there in the market. So if you had a really high quality ruby that was sent into the lab, chances are it was either from Burma or from Thailand or Cambodia. And it would have been easy to separate stones from those two deposits because the geology was very different between the two. So in Burma, we had sapphires forming in marble. So this is a limestone that's been metamorphosed into a marble. It's basically calcium carbonate rock. And you find rubies in these little veins cutting through the marbles. Whereas in Thailand and Cambodia, these are volcanic rubies. So they had some kind of igneous volcanic origin where they were formed in the presence of some kind of molten rock deep within the earth. And so needless to say, there's going to be very different properties between Burmese and Thai or Cambodian rubies. Now, all you would have to do is look in the microscope to be able to tell the difference. So Gubelin could have done this very easily back in the day with his microscope. He could have looked at a stone, a ruby. If he saw these nice iridescent flat platelet type silk particles as inclusions in the stone, he would have surmised that this is a Burmese ruby. On the other hand, if there was no silk, but you found these little melt relics, or these are kind of like little ancient blebs of magma that were trapped in these rubies when they were formed in that igneous volcanic environment. Now, if you saw something like that, possibly with one of these decrepitation halos surrounding it that had been kind of partially healed along the geometric crystallographic axes of the ruby, you would be able to conclude this is a Thai or a Cambodian ruby. The same thing holds for a lot of other stones. So emeralds are another good example. Again, back in the day when Gubelin was doing this, most of the high-quality emeralds would have come from either Colombia or Russia. And you would have seen very different properties. You would have seen very different inclusions in these two types of stones. So a Colombian emerald would have had that very classic jagged three-phase inclusion with a nice gas bubble, a little salt crystal in these fluid inclusions. And then a Russian emerald, something from a schist-hosted deposit, would have had more blocky two-phase inclusions, amphibole rods, micas, and possibly, specifically in a Russian emerald, these nice thin film interference patterns cutting through the stone. The problem is that sometimes geology fails us. So again, the hope is that the geology is different enough in two different deposits that you can have different properties from stones from these two deposits. But the problem is that's not always the case. So here's a good example. These are two inclusion scenes from a Sri Lankan sapphire on the left and a Madagascar sapphire on the right. And you can see that the inclusions are very similar between these two stones. So if this is all you had to go on, you have an awfully hard time trying to determine the origin of a sapphire between these two deposits. And here's really the main problem here. So the problem is, and Jim also alluded to this, is that nature doesn't really respect man-made borders. So those arbitrary lines we draw between countries, it doesn't really matter, especially not 550 million years ago when the Sri Lankan sapphires and the Madagascar sapphires were forming. In fact, at that time, the world was a much more condensed landmass. So we had this orogenic event, or this mountain building event, when we had two huge continents colliding into each other. So think about the current situation with the Himalayas. So the Himalayas formed when the Indian subcontinent crushed into the Eurasian continental plate and built up these huge mountains. It buried rocks to great depths and gave them enormous heat and pressure that created the gemstones deep within the earth. And then later, when these continents split up, the rocks were exhumed or brought up to the surface where the gems were liberated and were able to be mined by humans. So back 550 million years ago, when the Sri Lankan and Madagascar sapphires formed, we actually had Madagascar smack dab against Sri Lanka. So these two now currently disparate geographic locales were right next to each other when they formed. They had basically the same geological conditions of formation between these two deposits. So when we have situations where the geology is very similar, we have to look for very subtle clues to separate stones from these different deposits. I don't want to paint too much of a dismal picture of what's going on. There are certain things we can look for instance, in Sri Lankan sapphires versus Burmese or Madagascar sapphires or Kashmir sapphires. So we might see these nice hexagonal milky clouds in a Kashmir sapphire, which you could contrast with something in a Burmese sapphire where you'd see more arrowhead, iridescent, reflective silk. In a Sri Lankan sapphire, you might see the same kind of silk, but it would be more of an elongate, slender needles cutting continuously throughout the stone. For some stones, the microscope really isn't enough. So back in the day when Gubelin was doing this, he did everything with a gemological microscope. And that was really sufficient for what he had to do because there were far fewer sources that he had to separate. These days, we have stones like pyrite tourmaline, which come from 3 different sources, Nigeria, Mozambique, and Brazil. And unfortunately, for Palke tourmaline, there's really not any differences in the inclusion scenes between stones from different deposits. You might get needles and fluid inclusions, but they're going to be the same between these three different deposits. So we really have to turn to more advanced analysis, more high-tech instrumentation to be able to separate stones from these deposits. And here's just a really quick example. When you see like lab gemologists give talks, you'll often see these scatter plots with a bunch of little dots in a graph. And we might draw these little boundaries around the stones. So you might see these boundaries for Brazil, Nigeria, Mozambique. This is a plot of copper versus strontium. So copper and strontium are chemical elements trapped within the structure of these Palke tourmalines. One thing you'll also see, and one thing we don't maybe always explain very well, is this terminology here, ppm or ppmw, which means parts per million. Or you might see parts per million weight for ppmw. You might see ppma for parts per million atomic for specifically corundum. Now, I'm going to explain a little bit what that actually means. Imagine a swimming pool. So you're in Tucson at the end of the day, had a long day at the booth, you come back to the hotel, try to relax, and you jump in the swimming pool. It's a pretty big swimming pool. So the way to explain this nicely is that if you were to take one drop out of that swimming pool, one drop of water, that would be about 1 parts per million. So basically, if you put 1 million drops of water into the pool, you'd end up filling it up. And so the thing is, with these chemical plots that we show, you can really measure very, very small concentrations of different chemical elements very accurately and very consistently. And the way we do that is with this instrument. This is a laser ablation inductively coupled plasma mass spectrometer. And yes, that will be on a quiz at the end of the talk. And this instrument it allows us to measure very minute amounts of trace elements in stones like Palke tourmaline, sapphire, ruby, emerald, so on and so forth. And what basically happens is we have this laser ablation unit which focuses a laser on the girdle of a stone and removes a very, very small amount of material that goes through a plasma where the material is stripped apart into atoms and then ionized, and then it goes on to a mass spectrometer where we can basically measure the entire periodic table of trace elements in any stone that we want to look at. The problem is that this works for some stones, but it doesn't always work. So here's a scatter plot of the trace element discrimination plot of blue sapphires from metamorphic deposits. So that's Myanmar or Burma, Sri Lanka, and Madagascar. We didn't even include Kashmir in here because that would be too much. But you can see all of these spots in this plot basically overlap on top of each other in a big shotgun scatter. And so if we were to plot an unknown stone on this, you wouldn't really have much luck determining the origin based on these plots. So we oftentimes have to go back to the traditional methods to ascertain origin for some stones. A great example is this. These are kind of characteristic inclusion scenes in these metamorphic sapphires. These are the types of inclusions we look for in the lab when we're trying to understand the origin of a blue sapphire from one of these metamorphic deposits. So for Burma, you might look for straw-like nested silk, arrowhead silk. You might look for repeated twinning. For Sri Lanka, you look for the long, slender rutile silk, rectilinear fingerprints, and well-formed, nice carbon dioxide negative crystals. On the other hand, for Madagascar, you might look for banded milky clouds, kind of irregular and kind of chaotic geometric patterns in the stone, and etched tubes or graining. But again, the problem is sapphires can look similar from these different deposits. So these kind of characteristic inclusion scenes, there is some overlap between these three deposits in what you might be able to see. So for instance, that twinning that we've said is characteristic of Burma, you can also sometimes see it in Madagascar. Those rectilinear fingerprints that we saw in Sri Lanka that we think are characteristic of that deposit, you can also sometimes see in Madagascar. And then finally, those nice milky clouds that we often see in Madagascar sapphires can be seen in Sri Lanka and Kashmir and other stones as well. So the experience of a gemologist is crucial here. We need to look for as many different lines of evidence as possible to determine origin when we see inclusions like this. So we would look at the trace element chemistry, we would look at the multiple different types of inclusions in a stone, and the gemologist would have to reference their internal database and the database that Wim and his team have built up from the field gemology stones to help understand the origin of that stone. Now, I just want to kind of wrap this specific portion of the segment up with kind of a little plug of some new origin determination services that we've launched at GI recently. Within the last year, you may be aware, we launched jade, demantoid, peridot, and opal origin services. The last three were released just at the beginning of January 2026. And the field gemology program was really crucial in allowing GI to launch these new origin services. So these are photos of the demantoid mines in Russia, which we visited in 2019, Women I visited, and the Madagascar demantoid mines in 2023. And the samples we collected here directly from the mine, as much as possible, were the stones that we used to build the database of information about demantoid from different origins, so that we could, when a stone comes in the lab, we could determine the origin of that stone and put it on the report. Likewise, here's some photos from the field in Brazil at the opal mining fields in 2025, and at the Australian opal mining fields in 2012. And so we'd use those stones, we'd bring them back in the lab, get all the data, and we can generate plots like this. Obviously, we didn't really visit Iran because we're not allowed to visit Iran, but we actually had a colleague, an Iranian colleague who visited there and brought back some stones from us, kind of outside of the field gemology program. But with some of the other stones we collected in the field, and it shows like Tucson, the F-type samples, we're able to build up a database of Iranian stones, compare them to the Russian ones, create our scatter plots here, showing europium versus cerium, and showing some good separation between the Russian and Iranian stones there. Similarly, with opals, we can build the same kind of trace element discrimination plots and separate stones from Mexico, Ethiopia, Australia, and Brazil. This is a plot of magnesium versus aluminum. For peridot, we even have other kinds of discrimination that we can use to separate these stones. So we use a technique called Fourier transform infrared spectroscopy. Don't worry about that one. That's not going to be on the quiz. But we also see these very characteristic patterns from stones from different deposits for peridot. So where does this go next? I'm going to just really quickly wrap up with a kind of case study of field gemology and show why field gemology is still important and why it's going to continue to be important for decades into the future for gemology. This is a photo that Wim took of the Kanchanaburi sapphire mine in Thailand. And this photo was taken in 2017, which is important because it had been presumed to be inactive since the 1990s. So the Kanchanaburi sapphires used to be very big in the 80s and the 90s, but everyone kind of thought that the mine was more or less closed. But he went there and saw a lot of activity going on, a lot of sapphires coming out of the ground. And it was really important that he visited this old deposit. So one may have thought that it's not important to go to a deposit like this because it's pretty much closed, there's nothing going on, and everybody knows about these stones already. But Wim went and visited and got some samples from the deposit, which we analyzed in the lab, and it solved the major problem we actually had. So this is a scatter plot of basalt-related sapphires, gallium versus iron, and we frequently had basalt-related sapphires coming into the lab, which didn't match any of the stones in our reference database. So we had no reference for these stones. They didn't look like anything we'd ever seen before. But once Wim went to Kanchanaburi and collected those samples, we put them on our plots, and we saw right here at these low gallium concentrations, some of those Kanchanaburi sapphires were exactly lining up with these unknown stones that we had in the lab that we previously couldn't issue origin on because we didn't know where they were coming from. So what's next for field gemology is that we really need to go revisit old deposits. Sometimes we have deposits that are producing again when they may not have been producing for decades. There also may be differences in the properties of the stones that are being produced 10 years ago versus today versus 50 years ago. So revisiting old deposits is going to be very important for field gemology. We've been to most of the major deposits already, and what's going to happen next is just we have to keep going back to the old places we've been to keep continuing to collect stones and building up our reference database, collecting new stones from new deposits, and then simply building our database with more and more data so we can continue offering the most accurate origin services possible. And from there, I'm going to open up for questions, if there are any.
Questions? Yes, go ahead.
Yeah, hi there. For peridot, are you also doing origin determinations for once for meteorites?
So the ones from the meteorites will not get an origin report. They'll get a simple identification report. We've been offering identification of palistitic peridot for several decades already. So they'll continue to be treated the same way they've always been treated.
But they will be specified palistitic.
Yes.
Okay. And for the Sri Lanka versus for Vertriest, have you done age dating?
No, we've not done age dating. We don't. So the specific kind of LEICPMS we have in the lab is not super good for the age dating. It's better as a workhorse for standard trace elements. So it's not something we've really looked at yet.
Yeah, because Brazil, Nigeria, before the Atlantic opened, they're basically the same place. But Mozambique is a totally different place.
So my understanding is even though they're more separated from each other, my understanding is the general age of these three deposits is pretty similar. So that's actually another good point. Even though we don't have the capability, if we did, it's likely there wouldn't be big enough differences in the age between these three deposits.
Okay, third question is mainly for Wim. Back when they did the Kuprian feldspars that were baked, people were salting the mines, especially when the gemologists were coming to investigate. How are you worrying about or seeing any evidence of salted deposits?
Right, so this one's on. The question is about what do you do when mines are salted? Salting mines happens pretty commonly when there's visitors coming over that you just scatter a bunch of stones on the ground so it looks like an amazing deposit, which we've seen in a number of cases. This is something that we cannot avoid. It is something that we have to take into account. We are extremely critical about every sample we collect, and we routinely declassify stones. So we have actually a 7th grade of stones, which is a Z-type sample, which is where we completely get rid of any reliability of the origin. This happens quite a bit for stones when, in hindsight, we declassify them. That doesn't mean that these stones are useless. It just means that we can't rely on their origin label anymore. But they are still sapphires, so we can use them for sapphire projects. A common example was that a parcel of Burmese rubies that we bought in the market as D-type samples, when we came back to the lab, were able to polish the windows on them, look at the stones, we actually noticed that every single inclusion had an indication of heat treatment, which means that those stones were not untreated. We completely declassified them as Z-type samples. So that happens quite routinely, and that's the way we address that, where we are extremely critical of everything that we see and try to be as conservative in those grades as we can be.
Thank you both.
Thank you, Mary. Yes, over there in the.
Is there any cooperation or collaboration with any of the other laboratories, or is everything super proprietary?
In some cases, there are collaborations, especially when there are projects of mutual interest. Wim worked on a project with Lotus Gemology on heat treatment of Burmese rubies. So we do in some cases. There's a little bit of the master database we've built up is more of a proprietary thing, so we wouldn't collaborate in a way where we would share all of those data. But in the cases where someone has stones and they want them studied and they may not have access to some of the instrumentation that we have, yeah, we might collaborate with them on specific projects.
Yeah, I just want to add to that I think the challenge of sharing that data is that a lot of that data is dependent on how you collect that. If you use a different instrument, if you use a different calibration protocol, it might be difficult to correlate that data one-on-one from one location to another location or one organization to another organization. So that's something we also need to keep into account.
Kind of a follow-up. Do you think that, obviously this is a problem in the industry. I've had multiple situations where most recently a client had a quote-unquote cashmere sapphire from GIA, which then was rated as Madagascar by AGL, which then was rated by Sri Lanka by Google. So, and I see this not just once, but I see it quite often. And I'm just wondering if you think that there's a necessity for, in order to protect the consumer, to be a little bit more collaborative, maybe not in the proprietary element of the sets, but more of just
I think a lot of that is already being done. I think GA is, I cannot comment about how AGL and Gubelin looked at that stone and which procedures they used to come to their conclusions. But we are fairly confident in the way that we are doing things correctly. I think we've also been extremely transparent about a lot of the methodology that we use. I think especially with the Gems and Gemology winter issue from 2019, where we basically put all our cards on the table and said, this is what we got, this is what we know, this is how we do it. So we have been extremely transparent about that. There are discussions among laboratories as this as well. But again, like you said, this is not everything. Because there are challenges, there are proprietary informations as well there.
More questions? Yes, right here. Oh, okay.
So when I saw the photo of your hand with that itsy bitsy emerald, I just wanted to know what's the smallest size you can use?
That really depends on which technique you use. I think with trace element chemistry, those analysis spots, I believe, are 50 micron. So I think,
In like a quarter of a carat, a point,
well,
instead of micron, sorry.
yeah, that's going to be a difficult conversion. But I think it is also difficult to translate the weight and size of our research samples to stones that most of you are familiar with, because we mostly work with extremely thin stones. So they might be maybe only half a carat, but they might be almost a centimeter long because they are only half a millimeter thick. So it's difficult to compare that. I'm going to say that most of our stones that we use for inclusion purposes are 20 points and up. But for chemical analysis, we can go down to sub-millimeter sizes pretty conveniently.
Yes, right here.
Out of curiosity, has AI played into your research now?
We are dipping our toes in that, yeah. So we're not using like things you would think of like generative AI, but we use machine learning tools, which is kind of like under the umbrella of AI, to crunch the big data set we have. So, we look at these plots of the sapphire trace element chemistry and everything's overlapping, but there are cases with these big complex data sets where you can put it into a machine learning algorithm and it can find, subtle patterns that you may not see as a human looking at a two-dimensional plot. So we have some situations where we're using this. So specifically, currently, the jade origin that we're offering relies pretty heavily on machine learning tools. And we have some other cases where we're actively looking at implementing machine learning tools into this.
I think AI is mostly going to be increasing efficiency of the ways we look at data. It is not going to fundamentally answer the question of origin determination. But it is going to be a really good tool to help us look at things better. Like Aaron mentioned, like we rely very heavily on these 2D, maybe 3D plots occasionally, but that's where it stops for us as humans. While a computer can look at a 27-dimension plot, which is something that we can do for emeralds because we collect 27 variables. But as a human, we have problem processing all 27 at the same time, which a machine learning algorithm, it's literally built for that.
Well, it's complex too because in some cases what we're looking at is inclusions. And you have to have a gemologist with a fiber optic light and orienting the stone in the right direction with the light in the right direction to get a photo of a specific type of inclusion. And it's hard to find a way where you could take that and put it into a machine learning algorithm or recreate that kind of a process for something that could be automated. So it's complex because we sometimes have cases like with the blue sapphire, and we have experimented with machine learning there, and it'll give you an answer, and sometimes they may not always jive with what you're seeing in the microscope. So in cases where it's like mostly data crunching numbers coming out of a machine, it does tend to work pretty well. But finding other ways to introduce it is I think a little bit down the road. Yeah.
More questions? All the way back.
Yeah, so the question is what kind of microscope was being used to take the photomicrograph images. In most cases, that was probably specifically a Nikon SMZ 1500, which that doesn't really matter specifically, but it's a bit of a higher grade microscope than the typical gemological microscope a gemologist will have on their desk. So it will have higher magnification. Whereas like a gemological microscope on a gemologist's desk may go up to like 40x or something. This would go up to something more like 80 or 120x. We tend to think more of field of view, which is like the smallest field of view we would typically use is something like 1.26 millimeters for these photomicrographs. But basically, those photomicrographs were taken with a microscope that is more of a research grade scope, higher power than a typical one. But you should be able to see most of those types of inclusions in a stone coming across your desk. It's not high enough that it's out of the realm of possibility for you to see the same types of inclusions. And we use these higher grade scopes basically to get better photos. Because if you want to explain something or communicate information about inclusions, it's better to have nice, pretty photos.